right, day 19. Day 19, we're going to start out. This deals with the powers of algebra, finding a Pythagorean triple. So there's some things I need to go over really quickly before we start this lesson. And one of those is the Pythagorean theorem. Hopefully you remember this. If not, I'm going to show you. Guys, Pythagorean theorem deals with a right triangle. With sides A, B, C. You can use the Pythagorean theorem to find the missing side of a right triangle. The Pythagorean theorem is a squared plus b squared is equal to c squared. A and b can be switched, but c is always going to be across from your right angle. But this is the Pythagorean theorem. Alright? So let's look at the opening exercise. We're going to kind of go through this quickly. Sam and Jill decided to explore the city. Both begin their walk from the same starting point. So we'll let this be their starting point. And so it says Sam walks 1 block north. So he walks one block north, 1 block east, 3 blocks north, and 3 blocks west. All right, so this is where Sam stops. All right. Then it says Jill walks 4 blocks south. One block west, 1 block north, and 4 blocks east. So this is where Jill stops. So it says if all city blocks are the same length, who is the farthest distance from the starting point? It is not asking me who walked the farthest. It is asking me who is the farthest from the starting point. Okay? So you've got to think about this for just a second. Now, guys, I introduced you to Pythagorean theorem. So that probably means we're going to use this. I got to make sure I label our starting point. All right? This is our starting point. So I can create some right triangles here. All right? I'm going to draw just a dotted line here. And then look at this, guys. I've got a right triangle. I'll tell you what. I need an eraser. I need to draw it back to my starting point. Sorry, because we are going to, who is the farthest from the starting point? Okay? So who's the farthest from the starting point? So I can draw a triangle there. And now I can draw a triangle from where Jill stops. And we can look at our right triangles. All right? So, let's think about this. What is the length of this side? Well, 3, 4 is the whole side. And what is the length of this side? It is 2. That's my A and my B. So 2 squared plus 4 squared is equal to C squared. 4 plus 16 is equal to C squared. Guys, how do I solve for C? Take the square root of C squared and the square root of 20. So C is equal to the square root of 20. So that is the distance that Sam walked. All right, let's look at the distance that Jill walked. Jill, her triangle is 3. All right. And this is 3. All right. So I have this, I'm sorry, not the square root, but 3 squared plus 3 squared is equal to C squared. So 9 plus 9 is equal to C squared. So the square root of 18 is equal to C. So Jill walked the square root of 18. Now, I am not required to figure out what the square root of 20 is and what the square root of 18 is. Hopefully you guys can see who walked faster. All right, or I'm sorry, who was the furthest away from the starting point? Well, I was trying to find this part right here. I was trying to find this part right here, and I figured out that Sam is the furthest from the starting point. Okay? He is the furthest from the starting point because the square root of 20 is bigger than the square root of 18. Okay, so flip your paper over because we need to talk about, you guys did this a lot last year in geometry, but we need to state Pythagorean theorem, and then we need to talk about the converse of that Pythagorean theorem. So, Pythagorean theorem says this: if a right triangle has legs, of length A and B units, okay, we're not putting specific numbers in here right now. So if a right triangle has legs of the length of A and B units and hypotenuse of length C units, then A squared plus B squared is equal to C squared. Okay, so if-then statements, remember those. If a right triangle has legs of a length A and B units and hypotenuse of length C units, then I can say A squared plus B squared is equal to C squared. All right, so the converse of that. Do you remember what it meant to be converse? Switch them. And we're going to add just a little bit of wording here just to kind of help it make sense. So if the lengths A, B, and C of the sides of a triangle are related by A squared plus B squared is equal to C squared. Then the angle opposite the side of the length C is a right angle. that if I can use a squared plus b squared is equal to c squared, then I'm proving that it is a right triangle. Okay? We're going to be using the converse in this lesson. Alright, we're going to be using the converse in this lesson. Alright, so let's go to example number 1. Guys, you got to follow along in this, because if you don't, you're going to get lost. And I do not want you lost. Alright, so I'm going to walk you through this. In this example, it says, prove that if x is greater than 1, then a triangle with sides lengths x squared minus 1, 2x, and x squared plus 1 is a right triangle. Okay, so I'm going to draw it out. I want to know what they're saying. So my converse says if I have side lengths of A, B, and C. So if I have side lengths of A, x squared minus 1, B, 2x, and C, x squared plus 1, then I want to know, is this a right triangle? So I'm going to put a question mark there, because I don't know that I can draw that square corner there. Alright, so by the converse to the Pythagorean theorem, if a squared plus b squared is equal to c squared, then the triangle would be a right triangle. Alright? We are given that the triangle exists with these side lengths, so we do not need to verify that the lengths are positive. Guys, if we're dealing with lengths, we know they're going to be positive. Alright, so therefore we only need to check for any x is greater than 1, because remember it says if x is greater than 1. Alright, so for x is greater than 1, is this a right triangle? That's my whole goal in this question. Is it a right triangle? Alright, so let's set it up. So I know that it's telling me that I should be able to do x squared minus 1 plus, and I got to square that, plus 2x squared and that should be equal to x squared plus 1 squared. This, all I'm doing is substituting in. I've substituted my A, my B, and my C for the Pythagorean theorem. Alright, we are given a triangle with side lengths of 2x, x squared minus 1, and x squared plus 1. For some real number, the x has to be greater than 1. We need to show that the three lengths, 2x, x squared minus 1, and x squared plus 1, form a Pythagorean triple. Alright? So let's talk about how we do that. Alright. I need to, let's try to make this a little simple. I'm trying to figure out the easiest way to help make this simple for you. So the first thing we're going to do is we're going to show that 2x squared is equal to x squared plus 1 squared minus x squared minus 1 squared. So I'm going to take this over. I'm going to subtract this. So I want to prove that 2x and that quantity squared is equal to x squared plus 1 squared minus x squared minus 1 squared. Okay? Now, guys, look at this for just a second. Two x squared. I'm going to break this up for you because I want you to see something. Notice anything? Notice anything that we've talked about? I forgot to put my minus sign in there. Gotta put a subtraction sign there. Does it look familiar? I don't know. Are they conjugates? Maybe, possibly. Kind of look a little, interesting. So let's look at this. Go ahead and combine what's here. X squared plus x squared gives me 2x squared plus 1 minus 1, they cancel out. Alright. Guys, x squared minus x squared cancel out. 1 minus a negative 1 gives me a 2. Okay? So now I can multiply. 2 times 2 is 4. And I get x squared. Is that the same as this? Well, 2 squared is 4, x squared is 2. They are equal. So we have proven that 2x quantity squared is equal to 4x squared. So because they equal, then I have proven that yes, this is a right triangle. Okay? Like I said, it was kind of confusing. Hopefully, go back, rewatch it, look at it, and see what we were doing. It'd be easier if we had some numbers in there. Okay, so guys, any multiple of a Pythagorean triple is also a Pythagorean triple. We have what we call Pythagorean triples, and you are going to see these very often, especially if you take pre-cal or if you go into any kind of college math, you're going to see Pythagorean triples. Alright, so let's think about this for just a second. If I have, and this is one of the most common Pythagorean triples, I can have sides 3, 4, and 5. Okay? Now, that means that 6, 8, and 10 is also a Pythagorean triple. Why? Well, all I did here was multiply those by 2. That means that 9, 12, 15 is a Pythagorean triple. Because all I did here was multiply those by 3. Okay? So these are Pythagorean triples. Alright, they are multiples of 3, 4, and 5. Okay, so I also want you to understand that that can be a Pythagorean triple. Okay? Because they represent the same triple. Alright? We just refer to it as 3, 4, 5. All right. A Pythagorean triple is a triple of positive integers such that a squared plus b squared is equal to c squared. All right? So it is a triple of positive integers so I'm giving you your definition. Make sure you write it down. Gotta get my camera so that I can actually scoop my paper. All right? And we're going to just say those are A, B, and C. Such that A squared plus B squared is going to be equal to C squared. Okay? All right. So one way to generate a Pythagorean triple is to use this expression. So if you wanted to generate a Pythagorean triple, then let's say that I want to put 2 in there. All right? So we'll use x squared plus, or we'll use x squared minus 1. We'll use 2x, and we'll use x squared plus 1. So let's say I let x equal 2. Plug it in, guys. 2 times 2 is 4, minus 1, so that would be 3. 2 times 2 is 4. 2 times 2 is 4 plus 1 would be 5. So there is a Pythagorean triple. Okay? Let's say that I want to give x is equal to 4. So 4 times 4 is 16, minus 1 is 15. 4 times 2 is 8. 4 times 4 is 16 plus 1 is 17. So that would be a Pythagorean triple. So if you can remember this x squared minus 1, x squared plus 1, 2x, then you can create Pythagorean triples using whatever number you want to use. Okay? All right, example number 2. This example shows a clever way to remember that x squared minus 1, 2x, and x squared plus 1 can be used to find Pythagorean triples. All right, so it says next, we describe, sorry guys, it's really difficult to make sure it's in the camera and focused, and it becomes, this is a very difficult thing here. All right, so it says next we describe an easy way to find Pythagorean triples using the expression from example 1. Look at the multiplication table below for 1, 2 through 9. Notice that the square numbers 1, 4, 9, all the way to 81 lie on a diagonal of the table. All right? So, look at this. It says, notice that the square numbers 1, 4, 9, 16, 25, 36, 49, 64, 81, 100 lie on the diagonal of the table. What value of x is used to generate the Pythagorean triple 15, 8, 17 by the formula x squared minus 1, 2x, x squared plus 1? How do the numbers 1, 4, 4, 16 at the corners of the shaded square in the table relate to the values 15, 8, and 17? Alright, so it wants to know what value for x is used to generate the Pythagorean triple 15, 8, 17. Using the value 4 for x gives us the triple 15, 8, and 17. We already did that. We did that on the back. That's why I gave you the answer here, because you already knew. But let's talk about why, how, what are we doing here? So if you look at this, guys, they've shaded in this, and they want to know how does the 1, 4, 4, and 16 relate. Well, if you look at it, 1 is equal to 1 squared. 16 is equal to 4 squared. So we see that we can take 16 minus 1, that gives us 15. 16 plus 1 gives us 17. And then we have 4 plus 4 is equal to 8. That is our Pythagorean triple here. All right? So 1 is equal to 1 squared. 16 is equal to 4 squared. So here's my square. So I can do 16 minus 1, 16 plus 1, and then add my corners, my 4 plus 4. All right, so x would equal 4 gives us 15, 8, and 17. Okay? We already knew that. All right, so we see that 1 is equal to 1 squared, and 16 is equal to 4 squared. Okay, so that's where I get my square here. All right, so we can do 16 minus 1 is 15. 16 plus 1 is 17. And then, like I said, add your 4 plus 4 gives you 8. Okay, so now it says you try 1. Form a square on the multiplication table below whose left top corner is the 1, as in the example above, and whose bottom right corner is a square number. Use the sum or the difference of the numbers of the vertices of your square to form a Pythagorean triple. Okay, so I'm gonna take a pencil, we're gonna start at 1, and we need to go to a square. So let's go to 36. So I'm gonna shade in this. We want it to be a square. Okay, so now we've got 1, we've got 6, we've got 6, and we've got 36. Okay? So, what would I do here? Well, if 1 is 1 squared and 36 is 6 squared, that's a square. Alright, so I can do 36 minus 1 gives me 35. 36 plus 1 gives me 37. And 6 plus 6 gives me 12. So my Pythagorean triple should be 35, 12, and 37. Okay? 35, 12, and 37. Or I could write it, you could write it however you want. 12, 35, 37. It doesn't matter. Remember, the order of numbers does not matter. Alright? But this is a Pythagorean triple. I like the multiplication chart. I can use 49. I can go to 64. I can go to 81 if I want and create Pythagorean triples. I could use 4. I could use 9. I could use 16, 25, whatever. But I could create Pythagorean triples this way. All right? Now, how would I prove that? It says check the triple to see if it works. All right? So now I would have to know, how do I check that? Well, 12 squared plus 35 squared would equal 37 squared. Well, let's check that out. 12 squared gives me 144. 35 squared gives me 1225. And 37 squared gives me 1369. Well, is 1225 plus 144 1369? It is. So there we go. We've proven that this is a Pythagorean triple. All right. Let's generalize a square to any square in the multiplication table where two opposite vertices of the square are square numbers. So now they're not starting at 1. They said let's be able to just start wherever we want. But we have to make sure that we have square numbers. So 9 is a perfect square and 25 is a perfect square. Okay? How can you use the sums or differences of the numbers at the vertices of the shaded square to get a triple? 16, 30, 34. Is it a Pythagorean triple? So following what we did, okay, following what we did back here, 36 minus 1, 36 plus 1, 6 plus 6, let's do that. Let's see if that works. So 25 minus 9, 25 plus 9, and then 15 plus 15. Okay? So 25 minus 9 gives me 16. 25 plus 9 gives me 34. And 15 plus 15 gives me 30. Okay? So we would get the triple 16, 30, 34. So they want to know, is it a Pythagorean triple? Well, we would have to prove that. We would have to prove 16 squared plus 30 squared is equal to 34 squared. All right, so 16 squared is 256. 30 squared is 900. So 34 squared is 1156. If I add these together, guys, I get 1156 is equal to 1156. So yes, it is a Pythagorean triple. Okay? It is a Pythagorean triple. So it says use x instead of 5 and y instead of 3 in your calculations in part C. Write down a formula for generating Pythagorean triples in terms of x and y. Alright, so 25 minus 9 is the same thing as saying x squared minus y squared. Okay? Because 25 is 5 squared. So 25 minus 9 is generalizing or generalizes, let's use that word, x squared minus y squared. In other words, we can say we're going to substitute that in, all right, as the length of one leg. There's one leg. All right. The length of the other leg we did was 15 plus 15. Okay. So that generalizes to, this one's a little more difficult to think about, but what do we know about 15? 15 is 5 times 3. Five times 3 is 15. I got to multiply that by 2. So that generalizes to 2 times x times y, or 2xy. hypotenuse was 25 plus 9, which generalizes to x squared plus y squared. Because 25 is 5 squared, 9 is 3 squared. So, a Pythagorean triple can be calculated by use what we've got, x squared minus y squared. Alright, so x squared minus y squared, 2xy, and then x squared plus y squared. Okay? Not extremely difficult. Please make sure that you are looking at your vocabulary. That vocabulary is so important, guys. Extremely important. It is something we're going to be using throughout this year. If you have questions, make sure you reach out.